You know, when most of us see E equals mc², we think of a dusty old formula in a physics textbook. But that's not the right way to look at it at all. This isn't just an equation, it's a character. It has a life story, a really dramatic one, full of twists, brilliance, and even tragedy. And that's the biography we're going to explore right now.
I mean, this has got to be the most famous equation on the planet, right? It's a true celebrity. You could show it to almost anyone, anywhere, and they'd recognize it. But here's the thing. For all its fame, almost nobody knows its real story.
So what is the story packed inside these 5 little symbols? Well, it's an incredible tale of human drama, of mind-bending insights, and of a power so terrifying it would change the world forever. It's a story that we are about to unpack piece by piece.
Okay, let's dive right in. Before this equation could even be conceived, each of its parts, the E, the M, and the C, had their own origin story. They had to be discovered by some truly remarkable people, and often that discovery came at a terrible personal cost. So, let's start with M for mass. This is Antoine Lavoisier. He was this brilliant French scientist who, get this, conducted his world-changing experiments in his spare time. He's the guy who gave us our whole modern idea of what mass is. And the way he proved it was just so elegant. He took a piece of metal, he sealed it up inside a glass jar, and he weighed the whole thing very, very carefully. Then, he just let the metal rust inside the jar. When he weighed it again, the total weight was exactly the same. That's how he showed that mass is always conserved and never disappears, it just gets rearranged.
But here's the dark twist in his story. Lavoisier's day job? Yeah, he was a tax collector for the French king, and people hated him for it. He even built a huge wall around Paris just to make it easier to collect taxes. So, when the French Revolution kicked off, he was a marked man. He was arrested during the Reign of Terror and sent to the guillotine.
Okay, now for the C. The C comes from celeritas, which is just the Latin word for swiftness. For hundreds of years, figuring out its speed was one of the biggest challenges in science. Galileo tried, with lanterns on 2 different hills, but light was just way too fast. The real breakthrough came in 1676, when an astronomer named Ole Roemer was watching the moons of Jupiter and realized he could use their orbits to calculate that light had a finite, measurable speed.
And the speed they eventually figured out is it's staggering, about 670 million miles per hour. To try and wrap your head around that, imagine traveling from London to Los Angeles. Light makes that trip in less than 1/20th of a second. It's just an almost impossibly huge number.
All right, last piece of the puzzle. E for energy. For a long time, there was this huge fight in science about what energy even was. Was it mass times velocity, or was it mass times velocity squared? And the person who really helped settle the debate was an absolutely brilliant French physicist, who was also a championship fencer, by the way, named Émilie du Châtelet. She's the one who proved that the squared version was the right one.
So now the stage is set. We've got our cast of characters, mass, energy, and this giant number, the speed of light squared. We jump forward to the year 1905 in Bern, Switzerland, where a young, completely overlooked patent clerk is about to pull all these different threads together and change history. And that clerk was, of course, Albert Einstein. But I want you to forget the image you have in your head of the old genius with the crazy white hair. This was Einstein as a young man, whose own father was writing these desperate, heartbreaking letters to professors, literally begging them to give his son a job. Albert felt like a complete failure.
See, Einstein was obsessed with this question he'd had since he was a teenager. What would you see if you could actually catch up to a beam of light and run alongside it? And his conclusion was revolutionary. He decided, you can't. It's impossible. The speed of light is the universe's ultimate speed limit, and it's the same for everyone. And that one simple rule, it turns out, forces space and time themselves to stretch and shrink.
Then, almost as an afterthought, in this short 3-page note he added to his big paper on relativity, Einstein dropped the bombshell. He showed that mass and energy aren't 2 different things at all. They're 2 sides of the same coin. Mass, he said, is just a super concentrated form of energy.
For decades, the equation was mostly a scientific curiosity, something for physicists to marvel at. But it didn't stay that way. The idea grew up. And as the world entered the atomic age, the equation was suddenly thrust onto the world stage, and everyone saw its awesome and absolutely terrifying power.
So what's the secret ingredient that makes this equation so powerful? Well, it's all about that c², The speed of light, as we saw, is already a ridiculously big number. But when you square it, when you multiply it by itself, you get this, a number so huge it's hard to even read. That number is the conversion factor. It's the magic multiplier that shows how much energy is hiding inside even a tiny amount of mass.
Let me try to put that into perspective. If you could take just 1 pound of matter, anything, a book, a bag of sugar, and convert it completely into energy, you would release over 10 billion kilowatt hours. That's the kind of output you'd expect from a massive power station, all contained in something you could just hold in your hand. The secret to actually unlocking this power was figured out by the Austrian physicist Lise Meitner. She was the one who realized that when a uranium atom splits in two, the pieces that are left over weigh just a tiny, tiny bit less than the original atom. That little bit of missing mass hadn't just vanished. It had exploded into a massive burst of energy, exactly like Einstein's equation predicted it would.
In that discovery, well, it started a desperate race to build an atomic bomb. The Allies knew the Nazis' program needed something called heavy water, and there was only one factory in the world making it, way up in remote Norway. The first commando raid was a complete disaster, but then a second team, just 6 Norwegians on skis, managed to sneak in and pull off an incredible sabotage mission. And to finish the job, they later made the impossible choice to sink a civilian ferry that was carrying the last of the material to Germany, helping to halt the Nazi bomb project for good.
But the story of this equation isn't just about destruction. Not at all. It's also the secret of creation. If we shift our view from the atomic to the cosmic, we find that this very same equation is what powers the stars themselves.
You know, for the longest time, all the top astronomers believed the sun was made of heavy stuff, like iron. It just made sense. But in the 1920s, a young astronomer named Cecilia Payne came along and proved every single one of them wrong. She showed that the sun is made almost entirely of hydrogen, the perfect fuel for nuclear fusion. She was ridiculed for it at the time, but she was absolutely right.
And that discovery reveals the equation's true cosmic importance. Stars are basically just giant E=mc² engines. Every single second, deep inside the sun's core, hydrogen is being fused into helium, and a tiny fraction of its mass is being converted into the colossal amount of light and heat that makes all life on our little planet possible. So you have this incredible story of terrible weapons on one hand and life-giving stars on the other. But its legacy is also woven deeply into our modern world, into our technology, and into our fundamental understanding of the universe.
Now, seriously, think about this for a second. This smoke detector in your house, it uses a tiny bit of radioactive material, converting mass to energy. Hospital PET scans are basically E=mc² in action. Even the GPS in your phone has to constantly correct for the effects of relativity that Einstein predicted. If it didn't, it would be off by miles every single day. This equation isn't just history. It's invisibly all around us, powering our world.
So, in the end, you see, it was never just a formula. It's the biography of an idea that revealed the secret power of the stars and the incredible energy locked away inside every single atom. It's really the story of human curiosity, of our relentless need to figure things out. And it leaves us with one last big thought. What other incredible secrets are still out there, just waiting to be unlocked?